Hello. In this video we will look at methods for classifying data focusing on binary data. This section focuses on classification, especially binary classification. We start with a simple algorithm, the K-nearest neighbors algorithm. Next we move on to decision trees. We then see an ensemble method combining multiple decision trees into a random forest classifier. Then we move on to linear classifiers, the first being the naive Bayes algorithm. Then we see how to train support vector machines. We move on to another well-known and extensively used classifier, logistic regression. Finally, we see how to extend algorithms for binary classification to algorithms capable of multi-class classification. Our first learning system will be the K-nearest neighbors classifier. In this video, I describe the K-nearest neighbors classifier. I describe how the classifier makes predictions, important hyperparameters it uses, and problems faced by the classifier. Throughout, I will be using the classifier to predict the species of iris flowers. This notebook will be focused on using the K-nearest neighbors classifier. The first thing I'm going to do is load in the dataset. The iris dataset is provided with scikit-learn. It is one of their example datasets. It is a well-known dataset. So here I load in an object that contains the iris data and then save that into Python objects. And then I divide my dataset into training and test data. So here are the first 5 rows of the training data, and here are the first 5 labels of the training data. Now throughout this notebook I'm going to be doing a no-no. You aren't supposed to be repeatedly looking at the test set, and I'm going to do that throughout this entire section. The only reason why I'm doing this is so that I can give you some sense of how well these algorithms are doing on a test set. I am only doing this to demonstrate these algorithms, some things that you might be thinking about when you're training algorithms, and just so that I have some way to evaluate an algorithm without actually looking at how it's performing on just the training set, so that we can see, oh, it appears that this algorithm is overfitting, and other examples like that. In a real project, looking at the test set would be the very last thing that you do, right when you are presenting the results of your work to your boss. You would already have picked a classifier. There would only be one classifier that you're using. Getting statistics from the test set is only for academic purposes, so you have some idea of how your classifier is going to behave on your data set. You might have a test set that isn't actually the test set that you are free to look at as often as you like, but remember that every time you're looking at the test set, it is no longer acting as data that the algorithm has not seen before. Every time you look at it, that is now acting like seen data that is affecting the algorithm that you're training. So we're doing sloppy things in this video course, but that's just because I'm trying to teach you these methods and give you some sense of what's going on, and give you something to think about when trying to decide what algorithm you should be using, what you're looking for, things like that. Training a KN classifier is easy, loading in the training data. It will be used for every classification. Then we receive a new data point we want to classify. We compute the distance of the data point from each point in the training set. We determine the K nearest points. In this illustration, K is 3. The most common class amongst those nearest points is the predicted label for the point. So now let's see what this looks like in Python. We're going to use the K nearest neighbors classifier provided by scikit-learn. This is implemented in the K neighbors classifier class. So I import this class, and I create an object that will implement the K-nearest neighbors algorithm. In this case, I have a parameter and neighbors, and I'm setting this equal to 1. So in this case, K, the number of neighbors that you check, is equal to 1. And then I fit this algorithm, which in effect is just loading in the training data, and I demonstrate a prediction with this algorithm. So I provided it a point with a steeple length of 7, a steeple width of 3, a pedal length of 5, and a pedal width of 2. All of this is in centimeters. And it predicted the label 2, which in this case corresponds to the Virginica species. So let's go ahead and see what the prediction looks like on the entire flower training set. Notice that I get an array with a bunch of labels. These are all predicted labels. And I can see a classification report to see how well this algorithm is doing on the training set. And not surprisingly, it does perfectly. Why? Because the nearest point to an observation is the observation. So it's going to predict exactly the same label as that observation has. So of course it's going to have the perfect performance on the training set. There are two key hyperparameters for KNN classifiers. One is obvious, K, or how many neighbors to use when making predictions. The other is less obvious. How do we define distance between 2 points? Euclidean distance is not our only option, and in some situations such as text classification, we may want to use different metrics. We can use domain knowledge, which is our knowledge about the underlying problem we're trying to solve, to answer this question. We can also use cross-validation. With KNN, there are 3 problems to watch out for. The first is that you need to store the entire dataset in order to make predictions. The algorithm is memory expensive. This algorithm also uses a lot of computing power when making predictions, since a new data point needs to be compared to every data point in the training set to determine which are closest and thus make a prediction. Finally, KNN struggles when we have lots of features. This is known as the curse of dimensionality. In high-dimensional spaces, our intuitive notion of distance no longer describes the space well. It seems as if distances are large when there are lots of dimensions. So let's see cross-validation for choosing K. So I'm going to import a pandas data frame. These are my candidate Ks. I'm considering all possible Ks between 1 and 10. I'm going to create a dictionary that's going to contain the results of cross-validation, and this dictionary is eventually going to be turned into a pandas data frame. So let's go ahead and implement cross-validation. We're going to train this classifier for every possible choice of K. Now let's see the results. This is going to be a measure of how well our algorithm was performing. These are all the Ks that we tried along the rows. We have how long it took to fit data. We have score time, which tells us how long it took to get a score. And we also have the actual score for the classifier in cross-validation. And in this case, score is just going to be accuracy. Now, I don't want all that information. All I want is the test score. So here are the test scores for each run of cross-validation. These are all the different runs. Remember, we were doing cross-validation 10 times, so we have 10 folds, and each fold is held out in each run of the cross-validation and treated as a test set, while the remaining folds are treated as training data. And we can see the average performance of this classifier. It seems like we get good performance when we choose K equals 8. So let's see how our classifier performs in this case. Now we're looking at test data, and it looks like our classifier does pretty well for the test data. It doesn't make any mistakes on the test data set. So KNN did a very good job for this data set. And we can actually visualize what KNN is doing. I'm importing matplotlib, and here we see the observations. We have species being marked with shape. Black is the training set. Blue is correctly labeled training data. And we can see that every species that was predicted by the algorithm was the correct species. And we can see this for sepal length and sepal width. That's this plot. And we can also see it for petal length and petal width.